Redox reactions. This is the last topic in our lecture series, and we're going to start by taking a closer look at single displacement reactions. We're going to recognize ultimately that single displacement reactions are actually nothing else other than redox reactions, and then we'll move on to the slightly more complicated redox reactions. Alright, so single displacement. You may remember from our lecture on the different types of reactions that every time I was passing by a different type of reaction, you would see this slide. In particular, under synthesis, decomposition, and single displacement, you had the label redox, but I never really touched upon it until now. And the idea is that when you looked at your single displacement reactions, you had your one element by itself, which was neutral, and ended up displacing the cation in one instance. And when the element that used to be neutral combines now with the anion, it now develops a positive charge. And the change in charges is ultimately what tells you that you're dealing with a redox reaction. And by the way, redox stands for reduction oxidation. It's an amalgam of the two. It's a reduction, not reduction. It's definitely a truncation of those two words together. So that's what redox stands. Something is undergoing reduction and something is undergoing oxidation. So if you look at the charges, the one thing that you will need to keep in mind for the problems that I will give you is that oxygen is going to be 2 minus in charge, and hydrogen will be plus 1. Those will be the charges that will remain constant. If you were to have any of the group 1A, group 2A elements, then the charge will be equal to the group number of that element itself. For other elements where dual charges may be present, like iron, you might need to figure it out algebraically, which is what I'm doing right here. We have Fe2O3. Every oxygen has to have a 2 minus charge, meaning that it's really an oxide. And if you don't know what the charge of iron is, then you just put an X there. And really, all you want to do is multiply the subscript by the charge for each element present in the compound, and you want to add together all those charges such that you end up yielding the charge of the overall species. Now the overall species was neutral to begin with, so the 2 times x plus the 3 times minus 2 are at yield 0. And so when you solve for this equation, you see that 2x has to equal 6, which means that x equals 3. That's the charge of iron in the reactant side. Magnesium by itself, with no actual charge written, is automatically implied to have a charge of 0. Same thing for iron on the product side. And magnesium on the product side, if you don't know the charge, you could do the same thing. Oxygen will be 2 minus, put an X for magnesium, but hopefully by now you remember the magnesium is a group 2 element, so you should end up with a charge of plus 2 on magnesium. Alright, now here is the main premise. Now that we're looking at the charges, what we can see is that if we focus on iron, simply all you need to do is subtract the charge on the reactant with the charge on the product for the individual element that you're looking at. So here we have a charge of 3 plus minus a charge of 0, which tells you that you end up with plus 3. And what that basically means is that you have acquired plus 3 electrons. Alright, so you have gained electrons per iron center, as I may add. Alright, so we haven't even accounted for the fact that there's 2 irons present in the balanced equation. That's something we're going to do a little later. But yeah, so you have 3 electrons gained per iron. This is simply subtraction of the charges, 3 plus minus 0. And the way you could write this, if you want, is to have this little kind of connection, this line connection between the reactant and product. And based on the subtraction, you could say, okay, this is plus 3 electrons per every single iron that you have. Because you're gaining electrons, we call this a reduction. And another way to look at it too is that the charge is being reduced from 3 plus to 0. So that's another way to look at it. But the definition is that you're gaining electrons. That's what we depict as a reduction. Now for magnesium, there's a similar story. Subtract the charge of the reactant with the charge of the product. So you have 0 minus 2, telling you that you have minus 2 electrons in this process. In other words, you have lost 2 electrons per magnesium center. So we could write the same thing here for magnesium. Okay, so this is minus 2 electrons per magnesium center. And whenever you lose electrons, right, you have minus electrons, we call this the oxidation. All right, now taking a look at the balancing coefficients, right? Actually, before we do that, first things first, the species that is undergoing reduction is the species that is getting reduced. The species that is undergoing oxidation is the species that's getting oxidized. This is from the point of view of the reactants, right? So Fe2O3 is getting reduced, magnesium is getting oxidized. Now, because Fe2O3 is getting reduced, it will have to get reduced at the expense of something else. And because of that, we also can refer to the species getting reduced as the oxidizing agent, because the fact that it is getting reduced means that it has to have something else being oxidized. So it will promote the oxidation of something else, and as such, we call it the oxidizing agent. Same logic for magnesium. It will get oxidized in the process of this reaction, but it will have to get oxidized at the expense of something else getting reduced. So it will promote the reduction of something else, and as such, we call this the reducing agent. All right, the last thing is that if you look at the balancing coefficients, um, you do have a reduction, you have an oxidation, but the key premise of a redox reaction is that you have to have the same number of electrons being processed. In other words, you shouldn't have any free-floating electrons on either side of the equation. And so what that means is that to fully get the full picture of how many electrons are being processed, here's where the balancing coefficients come in. You actually have 2 irons present, so you should be multiplying the 3 electrons per iron by the 2 irons that you have present. And you have 3 magnesiums present, so you should be multiplying the minus 2 electrons per magnesium by 3 magnesiums, which basically cancels out the per iron and the per magnesium and yields 6 electrons on either side of the equation. So you have plus 6 electrons for the reaction, minus 6 electrons for the oxidation. And this particular feature is what we're going to be utilizing to balance oxidation reactions, redox reactions altogether. We have to have the same number of electrons being produced and gained. There cannot be any free floating electrons, or there cannot be lack of electrons, if you want to look at it that way. Alright, so in the next video, I'm going to start discussing solution redox reactions. So I'll see you then.